In this video, we're going to go over the valence bond theory in complexes. So if we look at our periodic table, okay, we have got some elements which are in between here. Okay, so these elements which are here are called D block elements. So this is block D, this region which we can see here. So amongst these elements, a lot of them exist with a multiple of oxidation states. Okay, so you see that some of them, like manganese, it will form plus, it will form 2 plus, it might form 3 plus. So they exist with a multiple of oxidation states. So such group D atoms or group D elements which have multiple oxidation states are called transition metals. Okay, transition metals. Any element that we are going to pick from the main group element. So this group, apart from this which I've shaded, the rest are called the main group elements. They've got only one oxidation number. Okay, only one oxidation number. But if you pick these elements which are in group D, some of them have got even 3, 4, 5 oxidation numbers. And such which have got different oxidation numbers are called transition metals. Zinc is a group D element, but zinc only has got one oxidation state. So zinc is not a transition metal, but it is a group D metal. That is because zinc only has got one oxidation state. Okay, though it is a group D element, it's not a transition metal. Now, so what happens is these transition metals are able to form compounds, and such are what we call complexes. So now group D elements, as we've seen, they've got a D orbital which is empty. Okay, so a D orbital has got 5 suborbitals. So they've got this D orbital which is empty, and so this D orbital can receive electrons, and that is what leads to the formation of complexes. Alright, so now what we need to understand about complexes, so what we are talking are coordination complexes. Maybe just to help us remember, if we talk of coordinate bonding is a type of bonding where one atom donates electrons while the other doesn't do anything. For example, when ammonia is reacting with this compound. Okay, so what is going to happen is this ammonia will donate its 2 electrons. This is not donating anything. So only the 2 electrons coming from ammonia will be responsible for the bond which will be formed. And so these 2 electrons are what will be responsible for the formation of a bond. So such is what we call a coordination bond, okay, or coordinate bond, where only one atom donates its electron pairs. So those are electron pairs which have been donated. Okay, very important to understand. And so this is what we talk about when you're talking about coordinate bonding or coordinate complexes. So when you're talking of coordination complexes, you've got a metal, and this metal has got empty orbitals. So it is going to react with another substance which we call a ligand, and this ligand is going to donate, not donating, let me not use the word donate, is going to share its electrons. Okay, because this ligand has got filled up orbitals, it has got free electrons. Okay, so those free electrons, like it might have a lone pair of electrons. For example, water is one of the ligands. So a ligand can be an ion or a molecule as long as it has free electrons. For example, water. Water has got free electrons. This is supposed to be hydrogen. So these electrons can be shared with a metal which has got empty orbitals. So in those orbitals which are empty, these electrons can feel coming together. Okay, and such leads to a coordination complex when a metal reacts with a ligand. So a ligand can be an ion or even a neutral molecule as long as it has got free electrons, such as even ammonia. Ammonia is also a ligand. That is because it has also free electrons. Okay. Alright. Now from this, let's go on and describe more what we are talking about. So we are saying a coordination complex are simply transition metals bound to metal ions, or let's say metal ions or molecules. We just say a ligand. Instead of saying metal ions or molecules, we simply say a ligand. So transition metal bound to a ligand is what we call a coordination complex. For example, we can have a transition metal cobalt. If it is bound to this ligand ammonia, it is bound to 6 of them. Okay, and then you've got 3 plus. So that 3 plus we can see there is just telling us the oxidation state for the cobalt which has reacted with the ammonia. So such is what we refer to as a coordination complex. So from here we can understand, so we've described the coordination complex, and then we've got also, let's try to see if we say coordination compound, what do we mean? So a coordination compound is simply a compound that contains one or more complexes. Okay, compound with one or more complexes. So such is what we call a coordination compound. For example, we gave a coordination complex which is above there, like that. So this is a coordination complex. This can again react with chlorine, 3 chlorine atoms. Such is a coordination compound. Alright. So it's simply a compound with one or more complexes. Alright. So the other thing we need to know is a coordination sphere. Now when you're talking of a coordination sphere, this is simply a metal and ligand bound to it. So if you've got a metal and ligand bound to it, is what we call a coordination sphere. Okay, such as you can have, let's say we've got a metal here and then you've got a ligand. Such is a coordination sphere. Okay, now these coordination complexes we are talking about have got a metal and also a ligand, and so these metals have got valences. So there are 2 types of valences which exist. We have got first the primary valence and also the secondary valence. We can have, let me give an example before even. So let's say we have got CO and then N83 6, okay, 3 plus. So if we want to determine the valence for this coordination compound, so the primary valence is the first valence we need to understand. Primary valence. So the primary valence is simply telling us of the oxidation number for the metal. Okay, oxidation number. Let's hope we remember ON, oxidation number. And then the secondary valence is simply telling us how many ligands are present reacting with the central atom, with the metal which is there. For example, in this one, we have got cobalt. If we want to determine the oxidation number for this cobalt, we are reacting with how many? We've got 6 ammonia molecules. Now, ammonia is a neutral molecule. Okay, so it has the oxidation state, the sum of the oxidation state is 0, and then it should give us the sum, which is positive 3. And so the oxidation state for cobalt in this compound is positive 3. So this is the primary valence for our cobalt. Now secondary valence, how many ligands are attached to cobalt? As we can see, we've got 6 ammonias. Okay, so we've got 6 as the secondary valence. Alright, so that is how we determine the secondary valence and also the primary valence. Now let's go in and see how we can use the valence bond theory to see the reaction which occurs. Okay, for example, if we've got nickel tetrachloride, okay, 2 minus like that. So in this case, the metal here we have is nickel, and then the ligand we have is chlorine. So remember I said a ligand can be an ion as long as it has got free electrons. So in this case, our ligand is a chlorine. So the first thing, if we want to see the reaction which occurs, we want to use the valence bond theory to determine the reaction which occurred. Is we need to determine the oxidation state for our nickel. So we've got nickel, which is reacting with 4 chlorines. Okay, now each chlorine has got an oxidation number of -1, because chlorine can gain 1, okay, electron. So the oxidation state is -1, and this should give us the total, which is -2. So what we are finding is nickel minus 4 should be equal to -2, and this is giving us nickel is equal to 4 minus 2, giving us nickel having an oxidation number of +2. So that is the oxidation number for nickel. So if we check on our periodic tables, nickel has got 28 electrons. Okay, so the electron configuration for nickel is argon, is the electron configuration for argon, and then we simply add 10 more electrons, because argon has got 18 electrons. Okay, we simply add 10 more, so that will be, in the 3D we are going to add 8, and then in the 4s we are going to add 2. Okay, like that. So now, because we are talking of nickel 2 plus, it means our nickel has lost 2 electrons. So it is still going to have the electron configuration for argon, but we are going to lose 2 electrons. Now remember, electrons are lost from the outermost shell. So this will be 3D, 8, and then 4s. So these 2 electrons will be lost, because we can't lose from the 3D. We can't lose from the inner shell before losing from the outer shell. So that will be 4s0. Okay. So now from here, now we can draw our nickel, the orbitals which are in nickel. So we've got the 3D and then 4s. Now remember, if we just talk of the 4th energy level, in the 4th energy level, how many orbitals do we have? We have got the s orbital, we have got the p orbital, we also have the d orbital in the 4th energy level. So in this case, we've only shown the s orbital, but we also have the p orbital and also the d orbital. That we need to remember. Okay, I might not show it. Alright, so let me just clean up the space inside. So in our nickel, okay, so the first one we have is the 3D. Now D has got 5 suborbitals. 1, 2, 3, 4, 5. So this is the 3D. And then from the 3D we have got the 4s. The 4s, the s, we know that the s has got only 1 orbital. And then from the 4s, we have got the 4p. Okay, we know that p has got 3 suborbitals. From the 4p, we can go to the 4d like that. Okay, now we can just end here. So here what we can see is that our 3d has got 8 electrons. So we fill in those 8 electrons. So we've got 1, 2, 3, 4, 5, 6, 7, 8. Okay, our 4s doesn't have anything. Okay, so this is our nickel 2 plus. Now it is this nickel 2 plus which is reacting 4 chlorine atoms. Okay, so this is now the ligand. It's reacting with 4 ligands. So what is going to happen is when it is reacting with those 4 ligand atoms, it is going to undergo hybridization first. Okay, so what we want to make sure is whenever something is reacting with 4 other things, this we need to know. Whenever something is reacting with 4 other things, it undergoes sp3 hybridization. So this is the hybridization that is going to undergo sp3. So 4s is going to be gotten, and then also these 3 are going to be gotten, and that hybridization is going to happen. So the hybridization is going to happen here. Okay, because the nickel is reacting with 4 different things, and that is the hybridization that happens. So what we are going to form is, we still have our 3d, it hasn't changed, and then these 2 are going to come together. Okay, so we've got 1, 2, 3, 4, and 5. And then you've got 1, 2, 3, and 4. So what we have here is still the 3d. So this one has undergone hybridization, and so the name now is sp3. Okay, we are starting with s and then p3 because the s starts and then the p is in front. Okay, so we have got already electrons here, and then we've got 1 there and 1 here. So this ligand has got, each of these ligand has got a lone pair. Now there are 4 ligands, so one ligand is going to donate a lone pair here. Remember, a lone pair has got 2 electrons. Another ligand is going to donate a lone pair there. Another ligand donates a lone pair there. Another ligand donates a lone pair there. So this now is what is going to be formed. So this is now our complex, which is nickel tetrachloride. Now at times they can ask us to determine the magnetic properties for the nickel tetrachloride. Now magnetic properties can either be diamagnetic, okay, diamagnetic, or paramagnetic. So when it is diamagnetic, it means all the atoms in the complex, all the electrons in the complex are bound. So each orbital has got 2 electrons. If it is paramagnetic, we can have an orbital which is not having 2 electrons. It can have 1 or less. So as we can see, this orbital has got only 1 electron. This orbital has got only 1 electron. And so this complex is paramagnetic. Okay. Paramagnetic. Let's hope that's the spelling, paramagnetic. Alright. Now, just looking at the hybridization, whenever we have got sp3 hybridization, the shape we have is tetrahedral. So nickel tetrachloride, this complex is sp3 hybridized, the magnetic property is paramagnetic, and then the shape is tetrahedral. What does tetrahedral mean? How does it look? Okay. So the way this compound is, we've got our nickel here, which is our nickel 2 plus. And then we've got the chlorines around it. Okay, so that is our compound, which is our nickel. Okay, I think the shape which I've drawn might look like square planar. So tetrahedral is, we've got something like this. Okay, sp3 hybridization, this is tetrahedral, where we can have so this is forming something like this. This is the tetrahedral shape we are talking about. Okay, let's look at another compound. We see what is happening. So now, the kind of hybridization which occurred there was sp3. That is what we need to know first. Again, the other thing that we need maybe to get to remember is which orbitals reacted. It is the s and the p3. There's one point which I'm going to talk about now. It is not going to work here unless I talk about another compound. So let's talk about another compound, such as, which compound can I even choose? Okay, let's talk of, let me try to look for another compound we see. Okay. Okay. We use the same nickel, but here we are using cyanide. Okay. In that case, -2. Now I want to see, by the valence bond theory, the reaction which is going to occur, and also the magnetic properties of the compound which we are going to form. Alright. So again, we need first to determine the oxidation number for our nickel, which is here. We have got nickel, sorry, and then we've got 4 cyanide. Now cyanide, each one has got an oxidation number of -1. So Cn, the oxidation number is -1, so it is Cn minus. And this should be equal to the charge, which is -2. And so this is giving us nickel minus 4 is equal to -2. So that will give us nickel. It will also be 2 plus in this compound. Okay. So actually the electron configuration for nickel 2 plus will be the same as the one we wrote in the first one. It will be 3d8 4s0. Now in this compound, the only difference is it is reacting with a strong ligand. Okay, so we've got strong ligands and also weak ligands. Strong ligands. Now strong ligands include the same cyanide. We've got cobalt. Okay, this is not cobalt, this is CO, like that. And then we've got En. And then we've got weak ligands. So the weak ligands include water, ammonia, hydroxide, chlorine ion, and these other ions. So those are weak ligands. Okay. So the behavior changes when a metal is reacting with a strong ligand, and also when it is reacting with a weak ligand. So let's see what is going to happen in this case. Because the same nickel in the first example we did was reacting with chlorine, which is a weak ligand. Now in this case it is reacting with cyanide, which is a strong ligand. So what is going to happen? So the same diagram is true even here. Okay. We have got firstly the 3D, then the 4S, and then the 4P. Three D has got 5 sub orbitals: 1, 2, 3, 4, and 5. got one. Okay, so this is our 3D. We are talking of nickel 2 plus here. Then this is our 4s and our 4p. So this one has got 8 electrons. Remember the electron configuration for nickel 2 plus. We should never forget that. It's the electron configuration for argon, and then 4s0 3d8. In the other one I started 3d8 4s0. It's really not different. Okay, so we first have 8 electrons here. 1 2 3 4 5 6 7 8. And then we don't have any electron in these others. Okay, now what is happening here, because we are reacting with strong ligands, this is a strong ligand which is reacting. Instead of us taking this just like this and then it undergoes sp3 hybridization, we first see in the 3d orbital, are all the electrons filled up? If they are not filled up, this electron which is alone is going to be pushed. Okay, it will be pushed like that. So that electron which has been pushed is going to be removed from that shell in which it is. Not from the shell, from the orbital in which it is. So we are going to remove it from this orbital. So it is going to go in this orbital here. Remember we had electron here and electron here, just remove them. Okay, so that electron has been pushed. So these are still 8, but we've just pushed the electron which was there. We've pushed it here because of this strong ligand which it is reacting with. That is why it will be pushed. And so now the reaction, because we are reacting with 4 different things, so the reaction, we are going to get the first orbital which is free. We want to form 4 orbitals. So we've got 1 2 3 and 4. So it is going to end up to here. Okay, so that is sorry, excuse me, that is the hybridization that is going to occur in this compound. So what we have is, we've got 3d, we've got these 3 which are completely filled up. Sorry, they are not even 3, there are 4 which are completely filled up. So we're going to put those alone. One, two, three, 4. So this is the 3d. And then these 3 which have reacted are going to also be, these 4 which have reacted are going to also come together. Okay, in that way. And then remember, we've remained with 1p orbital there. So the one which has remained will be here. So we've got, this is the p orbital. And then this one, this hybridization which has happened is from 1. Okay, we've gotten 1d. We've gotten 1s, which we can see here. And then we've gotten 2p. So this will be dsp2 hybridization. So remember, this one is completely filled up. Okay, and then this one which has undergone the hybridization is going to share electrons from now the ligand, the cyanide. So this ligand, each ligand has got a lone pair, brings this lone pair, but there are 4 of them. So all of them are going to bring their lone pairs like that. So such hybridization is called dsp3. Now, because we've used a d orbital in the inner shell, so the d orbital which has started from the 3d, so we call this as inner shell hybridization. Inner shell hybridization. Why are we calling it inner shell? Because if we talk of the 4s, 4p, we also have the 4d. So the 4d has just remained empty this side. We've not used it. Instead, we've opted to use this d which is from the 3s. From the 3d. So because we have used this 3d, instead of using the 4d, we call it inner shell hybridization. So whenever we see dsp2 hybridization, we've still reacted with 4 things. Remember, in the other hybridization we looked at, we reacted nickel with 4 things, but the hybridization was sp3. Whenever it is sp3, we said it is tetrahedral. But even if we've reacted with 4 things, but the hybridization is dsp2, this will be square planar. Okay, it is square planar hybridization. So now for square planar, how does it look? So the difference between tetrahedral forms something like that. Where I even showed this, it was like something like this. Okay, this is tetrahedral. This happens when the hybridization is sp3. Now, when the hybridization is dsp2, it is square planar, or we can say square planar. So in this case, we have got our nickel. These 4 things which have bonded will be in that way. Okay, so that is how it's going to be. So this is forming something like a square. Of course, this is looking like a triangle, but the angles here are the same. So that's why it's square planar. I should have just moved it much on top. Even this one maybe much down. Okay, so that is it. Now if we saw what we drew in the compound which we've just from drawing, all the electrons were paired up. We had the 3d, and then we had the dsp2, we had paired up electrons there. Even here they were all paired up. Even here they were all paired up. Okay, so because all the orbitals were completely filled, the magnetic property is diamagnetic. Okay, it is diamagnetic. That is, all the orbitals were having electrons which are paired up. Let's look at another compound, iron. Okay, reacting with this ligand CO. Alright, so now what will be the hybridization? The first thing we need to understand is the oxidation state for iron in this compound. So we've got iron plus. So this compound we can see here as a neutral charge. So even if there are 5 of them, times 0. And this we can see we don't have any charge there. So even this ligand is neutral. So we've got iron being equal to, okay, 0. So the oxidation state in this case for our iron is actually 0. So it is just a neutral atom which we are using. We are not using an ion for iron. We are using a neutral atom for iron. And so the electron configuration for iron, iron has got 26 electrons. So it will take that for argon, and then we add 3d6 for s2. Okay. So that is the electron configuration. So it has got 26 electrons. Argon has got 18. So we are remaining with, that should be, let me see if I'm not mistaken. Okay, so this is the electron configuration for our ion in this case. Alright, just that I don't have a periodic table to confirm with me. It's already written. So now in this case, now we are going to draw our ion. So we've got our ion there. We draw the orbitals. So we've got first the 3d. We know a d has got 5 suborbitals in that case, and then we've got 4s, which is only one, and then we've got 4p, where there are 3. I'm not just showing the 4d, but we are also supposed to put it. but it's just that for now we are not using it. We'll see it later. 4s and then 4p. So in the 3d we've got 6 electrons. 1, 2, 3, 4, 5 and 6. And then in the 4s we've got 2 electrons. Now because this compound which we are reacting with the ligand is a strong, this ligand which we are reacting with ion is a strong ligand, all these electrons are going to be pushed so that they pair. Okay, starting from the 4s, they are all going to be pushed so that they make sure that they pair. So what is going to happen is, so in here it's only this one which is filled up, it's only this orbital which is filled, so this electron will be pushed here, so it is going to come in this orbital like that. So in here we don't have anything, and then these 2 electrons which are here are going to both of them be pushed here, so we are going to have there and there. So it means this and this will be empty, and then those 2 electrons are also going to be pushed in this one. Let's hope we've seen what is happening. Okay, so what is happening is this. Let me first maybe get this. So we are going to have this, we are going to bring it here, and then this other electron will bring it in here, and then this one we are going to bring it in here. So this orbital which is here is going to be empty. Okay, and then these others are going to be filled up, so the other one is going to be empty. So that is what we are seeing here. So this one is going to be empty, and then this now will remain also empty. Okay, let me maybe draw a different diagram instead of labeling this one. So we are going to have alright, so let me just remove them as I showed earlier. So this one is going to be empty, the last orbital in the 3 will be empty, and then the 4s will also be empty. So those are going to pair up here. We are going to have paired up like that. So now because we are reacting with 5 things, okay, like we are reacting with this ion with 5 ligands. So what is going to happen? This one is paired up. Okay, what is going to happen is we are going to get this starting from this orbital which is empty. We are going to make sure that there are 5 going this way. So it is going to reach up to there. So these are going to merge. So that is going to form an hybridization. Okay. So there will be 5 of these. 1, 2, 3. Let's hope there are 5. So this is the 3D. Remember we only had 1, 2, 3 and 4 which had paired electrons. So those are the ones we are putting here. 1, 2, 3, 4, 5, 6, 7, 8. Okay. And then the others which have remained, we've gotten 1D. So that is D. We've gotten 1S, that is S, and then we've gotten 3 P's. So P3. So this is the hybridization that has occurred. DsP3 hybridization. Okay. So each of these ligands is going to bring 2 electrons. So each ligand brings 2 electrons to the ion. Each ligand brings 2 electrons to the ion. So we are going to have 2 there, 2 there, 2 there, 2 there, and then 2 there. So this is our ion. Okay, this is the ligand which we have. So this is the diagram for the ligand. Now from here we can determine the magnetic properties. As we can see, all the orbitals have got 2 electrons. Even here they have got 2 electrons. So the magnetic property, this is the magnetic. Okay, is the magnetic. What of the molecular geometry? What will be the geometry? Now whenever we've got this type of hybridization, DsP3, whenever we've got DsP3 hybridization, we need to know, just like when we have got sp3, it is tetrahedral, dsp2 is square planar. Whenever we've got dsp3, the hybridization here is bipyramidal geometry. Okay, that is the molecular geometry. It's bipyramidal. Actually, I've even left the word here. It's trigonal bipyramidal. Okay, trigonal dipyramidal. How does that look like? So we've got iron here. We reacted with CO. You've got CO, then you've got CO, another CO, then CO. We've reacted with 5 things. Okay, so this is going to form, first at here we're going to have something like a triangle, and then you've got on top it comes like that. So what we can see is a pyramid on top, and then even down is going to form a pyramid. So because the base here is a triangle, that is why we call it trigonal. And then bi means we have got 2 pyramids. We've got on top and down. So whenever we got DSP3 hybridization, it gives us the trigonal bipyramid. Okay, let's look at another compound. Let's say we talk of, so same here we saw that the electrons, we got a d orbital, which is from the 3D. That was also inner orbital hybridization. Okay, now what if we talk of chromium also with CO? Now we've got 6 of them. So the oxidation state for chromium here, just looking at it, will be 0. So we are using a chromium atom. So the electron configuration for chromium in this case is going to be that of argon, and then we add 3d5 4s1. So chromium is one of the exceptions to the rules which to the rules of filling orbitals. So because we are supposed to fill first the 4s with 2 electrons and then go to the 3d. So actually we expected the electron configuration for chromium to be that of argon, and then 3d4 4s2. But this is not the actual one. This is the expected one, where we first fill the 4s because it has got lower energies than the 3d. But that is not what happens. We first fill the 3d. We only fill the 4s with 1 electron, and then we go to fill the 3d. So we've only have 2 exceptions, chromium and also copper. Okay, instead of first filling the 4s, we first fill the 3d with 10 electrons. Alright, so that is it, the electron configuration. So we are going to draw the orbital diagram for our chromium. We've got first the 3d, we've got the 4s, and then the 4p. Okay, the 3s, I mean the 3d, there are 5 suborbitals like that, and then the 4s is only 1. And then this one, there are 3 of them. So we've got a 3d, 4s, and then 4p. This is a strong ligand. Let's remember that. So we are filling first with we are filling the 3d 5 electrons. So we've got 1, 2, 3, 4, and 5. And then the 4s, we have got 1 electron. So what is going to happen is the electrons are going to be pushed because we are reacting with a strong ligand. So this electron which is here is going to come and pair up with this one. This electron here is going to come, pair up with this one. This electron here is going to come and pair up with that one. So what you are going to have is these 2 orbitals and this one. They are going to be empty. Okay, so those are going to be empty. Those electrons are going to come here instead. Let's hope we know how it has come. I've shown that. Alright, so now because we are reacting with 6 things, so we are going to start from this point. We are going to make sure that the orbitals are 6. We are going to reach up to this point. So these are the orbitals which are going to mix. So here we're going to remain with only with only 3 orbitals, and then these are going to mix the 6 of them. Okay, this is the 3D having 6 electrons all paired up, and then we've got 6 orbitals that has come due to hybridization. 2, 3, 4, 5, 6. Okay, 1, 2, 3, 4, 5, 6. All right. So now looking at this compound which we got 2d orbitals from the 3d. So we got 2d, so d2, and then we got only one s, so s, and then we got 2 from the p. Okay, so we formed d2sp2 hybridization. So each of these ligand is going to bring its electrons and then fill these up. So one ligand brings 2, one ligand brings 2, one ligand brings 2, another one 2, another one 2, another one 2, like that. So this is our now chromium, like that. This is the orbital diagram now for the actual one which is formed. So what we are having here is all of these orbitals have been filled, they've got 2 electrons, all of them. And so the magnetic property is diamagnetic. Diamagnetic. Okay. And then the other thing we need to talk about is the geometry of our compound. So what will be the geometry? So whenever we have got D2sp2 hybridization, whenever we've got D2sp2 hybridization, the geometry form. So D2sp2 hybridization, the geometry is octahedral. Octahedral. Okay. So what we are having is we have got chromium at the middle, at the center. And then we've got this compound here. It is also here. It is there. It is there. It is also there. And then also there. So this is going to form something like okay. So this is what we have, and then to the central metal, like that. So this shape is what we call an octahedral shape. Now as you can see, our base here, this is supposed to be a square, not a rectangle as we can see it. Okay, that is a square. And then on top we've got a pyramid, a square pyramid, even down a square pyramid. So this octahedral is square by pyramid. We've got a square here and then a pyramid on top and down. So octahedral is square by pyramid. So that is the molecular geometry. Okay, let's look at a last example. Then we are done with our valence bond theory in transition metals or in complexes. Okay. So we can look at something which is, so even that one which we've looked at is inner orbital hybridization, because we used the orbital from the 3D. Okay. So what we are going to use here now, let's try to use our ammonia. We see what is going to happen. Okay. Let me try to look for a weak ligand so we see which one to use. Okay. Let me of course use ammonia. We know that ammonia is a weak ligand. It might not be always. At times it can be a strong ligand. It might not be always. Alright. Now in this compound which I'm drawing, it acted as a strong ligand, but it's a weak ligand. Okay. Though not too weak. So that is even depending with the compound that is reacting with. But mostly ammonia, water, even chlorine ion, all those are weak ligands we can talk about. Alright. Okay, so let's look at this compound. We see what is going to happen now in this. What will be formed, the kind of hybridization which will be present, what will be it. Okay, we've got 6 of them, and then let's say let me use another metal in this case. Let's say if I use iron and then the complex we are forming, let's say it is to the 3 plus. Okay, what will be the compound formed? So we've got iron in this case, and then reacting with 6 ligands. Ammonia is a neutral molecule, and that is giving us 3 plus. So it means our ion has an oxidation state of 3 plus. Okay. Okay, it has got an oxidation state of 3 plus. So iron itself, it has got an electron configuration of argon, and then 3d6 4s0. So having 3 plus means it has lost 3 electrons. So first is going to lose these 2 electrons, and then 1 electron it will lose from that one. So iron 3 plus will be the electron configuration for argon, and then 3d5 4s0. Okay. So from this one we are going to have this is our 3d, and then we've got 4s not inside. Okay, we've got 4s there. We've got 4p, and also we've got the 4d. One, two, three. Okay, there are also 5 there. So in the 3d we've got only 5. 1, 2, 3, 4, 5. We don't have anything here, not anything anywhere. Okay. So now because we are reacting our ion with a weak ligand, instead of these electrons being pushed, they won't be pushed. In case our ion would rather go and react just like this. So these ligands are going to take up only empty orbitals. So these which are already filled up, instead of us making sure that these pair up, they will not be able even to pair up. Okay, they will not be able to pair up. So what we are going to have is, let me use 2 plus here, so that our ion is only going to lose 2 electrons. Okay, not even 2 plus, let's say. Okay, yeah, let's use 2 plus in this case, so that I describe it properly what is happening. So I'm using 2 plus there. Okay, so this 2 plus we are using, it means we've only lost 2 electrons from this one. Okay, so we can see that these are remaining, there will remain 6 of them. So that means we've got 1, 2, 3, 4, 5. I wanted to make sure that the electrons which I have here are odd, but I just discovered they are already odd because we only have 5 electrons there, so it is fine. Instead of me pushing this one here this one here. Okay, we can still use the actual one which we had earlier, so I haven't changed anything. I just wanted to make sure that the electrons are odd. This is already an odd number. Alright, so what we are going to have is, because this is a weak ligand, instead of us pushing these electrons, we would rather, because there's no difference for us using this d orbital and this d orbital, all of them are d orbitals. So instead of using this d orbital by pushing this, we are just going to start from our s orbital here. We want to form 6 orbitals, so we're going to go all the way from the s orbital up to here. Okay, like that. We would have pushed this one here and pushed this one here, and so instead of going to pick these 2 orbitals, we would have picked these 2 orbitals which are here. But because this is a weak ligand, we would rather go to pick those which are already empty that side. Okay, so that is what is going to be happening. And then we are going to still have so notice that we are going to remain with 3 orbitals there after those hybridized. So these would be 3 still here. So these are still the 5 of them. 1, 2, 3, 4, and 5. And then these are now 6. We've got 1 here, 2, 3, 4, 5, and 6. Why are they 6? Because we are reacting with them 6 ligands. So we've got 1, 2, 3, 4, 1, 2, 3, 4, okay, 5 and 6, and then we've just remained with 3 that side, so there are 3 here. So this is the 3D, but here the first one we got is the S, and then we got 3 P's, and then we went to get 2 D's. So if we started with this one, it would have been D2sp3, but because the D we've gotten is from the 4D, it is sp3d2. So the kind of hybridization which has happened here is outer orbital hybridization. Outer orbital hybridization. Why? That is because we've opted to use the 4D instead of using 3D, but all at the same time is a D, so there's not really any difference. Okay, so here they are still empty. Okay, these are still like this. There are still 5 of them. We haven't changed anything. So now this one which has been hybridized, each orbital is going to gain 2 electrons from each ligand because we've got 6 ligands. So the first ligand brings 2 electrons, second ligand, third one, fourth, fifth, and also the 6th. And so this is our complex which we have ion. Okay, 3 plus. So that is our complex then. Now the magnetic property for this one, because we've got these orbitals which are empty, which have got only 1 electron, so the magnetic property for this one is paramagnetic. So whether sp3 d2 or d2sp3, they all have the same molecular geometry, and that is octahedral. So even in this one, the molecular geometry is going to be octahedral. Hybridization is sp3d2. Okay, so we end here for the valence bond theory in complexes. Thank you so much for watching the video. Hope it was helpful.